All right, so growth rates of functions. Well, so this is more like, in a way, a pattern recognition type of topic based on what we have done right now with all the L'Hopital's rule. For example, what if you're given like a really ugly looking limit to evaluate? I don't know, maybe limit x to the 3017 over x to the 17 ln of x to the 1000. Of course, you don't want to do L'Hopital's rule 3017 times. Do you want to do that? No, right? However, well, we're going to use the ranking of functions in order to, um, in a way, by just looking at this limit, okay, see which one grows faster than the other one, and then see, okay, this limit will be 0 or this limit will be infinity. And also, well, so for the next definition, so suppose we have two functions f and g that we want to compare. So what's going to happen here? Well, so our reference function typically is a function f. The next other functions like g, h are just like secondary functions. So primarily f is our primary function. Well, so if we set the limit this way, where the numerator is f and the denominator is g, well, if the limit in the end it's an infinity, well, that means in the numerator we have a function that grows faster than the one in the denominator, right? Or on the other hand, if we set it up the other way, g over f, well, in this case, if the limit is 0, that means that the function in the denominator is going to grow at a larger rate, and well, for a larger values of x, limit is 0. Now, when we have f over g, but in this case it's not a 0, it's not an infinity, that means that these two functions are comparable by a factor of k. For example, I don't know, maybe we get a limit of 3. Well, that means that f grows 3 times with respect g, right? So let's have a look at some examples and see how these functions behave. So on the one hand, f of x equals ln of x, g of x equals f equals x to the p power. Well, notice in this case we don't have numbers. We just have the symbol, the letter p that denotes some integer power. Or yeah, mostly yes, actually integer powers. Otherwise, with rational powers, we're going to get in trouble. So, well, by looking at these two functions, well, let's see, ln of x versus x to the p power, for example, x squared or x cubed, x to the 7, just looking at both functions, which one grows faster, ln of x or x to the p? X to the p, right? So let's have a look at this individually. Okay, so on the one hand, let me write limit f of x in this case, or ln x approaches infinity, that's infinity, and limit x approaches infinity of ln, not an ln, that's x to the p power. That's also infinity. Well, like x squared to infinity to the 5th, infinity to the 7th, well, it's just a larger infinity every time. Even for p equals to 1, the linear function grows faster than the logarithmic function. The logarithmic function grows at a steeper rate just for smaller values of x. But then it just gets a little more bounded or apparently asymptotically, even though it's not asymptotically. All right? So let's see. Let's compare this. And let me set up the problem this way with the f on the top. F of x over g of x. All right? So what are we going to have? So limit x approaches infinity of, what did I do? F? Yes. Okay. ln x over x to the p power. Well, in this case, we already got the infinity over infinity. Let's do the L'Hopital's rule. So that's limit the derivative of ln x, that's 1 over x, and the derivative of this x to the p, that's px to the p minus 1. That's essentially the general power rule. What did we do here? L'Hopital's. And let's try and simplify this expression right here. So let's see what we're going to get. I'm going to write this x in the denominator. So that's going to be px times x to the p minus 1, 1 over that. And well, do you see this invisible power for x, which is 1? And we also have the same base here, x times x. What do we do with the bases when we have the same, well, what do we do with the exponents, rather, when we have the same base?
Add them.
Add them. So what is going to be 1 plus p minus 1? So px to the 1 plus p minus 1. Well, the 1's cancel, and we will be left with px to the p. And well, what's the limit at infinity? Where is this going to go? 0. All right? So which case do we have? In this case, it's the g of x. Whoops. Grows faster. All right? And well, of course, between the exponential function and the polynomial function, well, that one just gets really steep for smaller values of x, except for negative values of x. Well, that just go really, really slow. So, but in this case, we're looking for positive values of x. So that's the condition here, right? And that's what we want. We want to see the end behavior of this function for larger values of x, so no negative values in this case. All right, so in a similar way, limit of v to the x and limit of x to the p. We already did the x to the p, and actually both are infinity. So let's set it up. Limit f of x over g of x, and that's the limit e to the x over x to the p as x approaches infinity. All right? So what's going to happen here? Well, L'Hopital's rule again. The derivative of e to the x, which is itself e to the x and px to the p minus 1. All right? But there's a little issue here. Well, I mean, the e to the x is never going to disappear. All right? So in this case, let me give a value for p. You know, the simplest one possible. E to the x. Let's take the case for x squared. So limit e to the x to x. And by looking at this ratio between e to the x and to x, what do we have? Isn't it the infinity over infinity again? Okay, that means L'Hopital's rule apply again. And in this case, well, infinity. That means in this case, which one grows faster? Isn't it e to the x or f of x? All right, so of course we don't have to do all this for every single kind of function. On the next page, we have a couple of plots, we have a couple of graphs that show the behavior of the most general or the most common graph. You know, so let's compare, you know, like the linear function y equals mx. Let's keep the plus b. take the simplest case where the x-intercept is at the origin, right? So, well, the only thing that we're going to change in here or control is the value of the slope. And well, the steeper the slope is, well, the faster that it's going to grow. But still, even if the slope is really big, compare it with a polynomial form. But be careful here because x to the p and y equals mx, they're both polynomials. Even though we always mention the linear function as a linear but not a polynomial, but it is a polynomial. We talk about polynomials when powers are 2 or higher, right? But I mean, see what happens here with x to the p. The x to the second power, parabola, x to the third power, the S-shaped function, And the higher the power, the faster they grow with respect with the linear function. And then what do we have? Exponential functions versus polynomial functions. And again, even though polynomial functions for higher powers, yes, they grow faster. Yes, in this case, it is the exponential functions, the one that are larger in value. And of course, let's look at this definition right here. So in this case, this is the ranking of all these kinds of functions that we usually deal with, and the ones that these are in this case, written from smaller to large in terms of the growth rate. So the one that grows at a slower rate is the logarithm function. Even to a power grows slower than a polynomial, and then the polynomial grows faster, and then polynomial times logarithmic grows faster, and then the product of two polynomials here, like for example, if you have x to the p times x to the s, that's x to the p plus s. And in this case, for example, x to the 3 times x to the 5 and x to the 3. So what are we going to get? X to the 8. Of course, x to the 8 is going to grow faster than x to the third, right? Yes?
Where will e to the x fit in?
The e to the x, it's going to fit in here in the b to the x.
Okay.
Where b is any power 2 to the x, 5 to the x, any power including the natural exponential value, all right, Euler's number. And of course, the largest one would be x to the x power.
All right. The factorial
Yes, I think I didn't look through that, but yes, for sure the factorial should grow a lot faster that you wouldn't even be able to look at it. I just tried to compute the factorial, I believe 13, 14 on the calculator. I think the calculator doesn't even output that value, right? It's really big. And well, so let's have a look at some examples, and of course, check this kind of exercises. Do you want to do the L'Hopital's rule for this? Some of them are not that bad, though some of them are doable. But in this case, the idea is that we'll look at this ranking of functions in terms of the growth rates. And of course, let's have a look at letter A. So what do we have in the numerator? We have a polynomial over an exponential. Which one grows faster? The polynomial or the exponential? So the denominator is larger, the limit is 0. All right? And this is just by looking at the limits, not even checking for an indeterminate form, doing L'Hopital's rule. In this case, how many times? 3 times. No, we don't need to do that. Okay, what about letter B? Exponential in the numerator, polynomial in the denominator. 0 or infinity? Infinity. What about ln of x versus x cubed? Ln in the numerator, x cubed in the denominator. Again? 0. All right. Okay, how about you guys do letter D from letter I? Take a couple minutes, have a look at those, and we'll look at them together. Of course, talk to the person next to you, compare results, share ideas. Raise your hand if you have any questions. All right, letter D. What do you got for letter D? Infinity, all right. And do we agree with infinity? Yes? Okay, someone else, a letter E. What's your name? Luciano, I think is your name? Okay. Infinity, all right. I think I agree with infinity. Okay, letter F. What's your name? What's your name again?
May.
Okay, May, yes. May, what you got for letter F? You get 0. I think in this case I got, oh, that's an interesting one. All right, because in this case, well, we have the logarithmic in the denominator, and in the numerator we also got a logarithmic, but that logarithmic is multiplied by a polynomial, which I think is going to make it grow faster than the one in the denominator. So this means this will be infinity. Okay, what's your name? Anna, I think is your name. Okay, what you got for letter G? 0. Okay. All right. Right next to Anna, what's your name?
Shara.
Shara. Oh, yeah, Shara. What you got for letter H? Infinity. Yes. Yes, of course we have a polynomial here. Yes, looks higher in degree than the one in the numerator, but the one in the numerator has a factor that contributes to the rate of growth, which is a logarithmic. Of course, maybe at a smaller rate, but still contributes some. And last of them, okay, next to Shara, what's your name again?
Laylee.
Laylee. Yes, what you got?
I think it's infinity.
Infinity. All right, let's see what we have. So we have an exponential e to the 100x. Yes, it's really big. But the denominator, it's an x to the x, which is also actually bigger. So this should be 0. Yep. Sounds good? All right.